Hello everyone. Here in this quick video, I will comment on the solution to question 18, part 3. That's the one which has to establish the projection of this region. So here it is. Here's the region we have in this question. This is about the cone. That's the cone, and inside the sphere. If you've done the previous parts, part 1 and part 2, you probably know that this is the section of that region. So this is a sphere, and this is a cone. So we're looking at this ice cream cone, above the cone and inside the sphere. And we need to project it down and find out what's going to be here at the bottom. If you played around with these two surfaces in the emulation software like GeoGebra, you probably know the projection will be a circle, but we need to formally establish the circle analytically, and this page or this video will show you how to do that. So first I will quickly describe what the projection is on the plane z equal naught. The formal description of the projection is this. This is the collection of all points on the plane. You see, I don't mention z anymore because z is 0. It's a collection of all those points on the plane for which you can find z such that if you make a triple out of these 3 points, this triple will be in this set. That's the formal encoding of the idea of a projection. It's a point here such that you can find somewhere above it for some z. At some stages maybe multiple z's. For some points it will be just one z, which works like this, but at the very least it must be one z such that if you make a triple it will be in the set d. So the key to the analytical solution to this problem is to provide another alternative description to the domain D. Okay, and that's what I'm going to do. Look at this. First I'm going to just work a little bit on this sphere or ball description. See, I just extracted the perfect square and then I solve for z. It's a very typical transformation you do to an equation of a sphere or an inequality of a ball. See? So first I completed the square in here, and then I solved for z. That's the solution. The solution with the plus, that's the top hemisphere. The solution with the minus, this is the bottom hemisphere. For the cone, we just take a square root. So if you accept these solutions, then my alternative description for the set D, alternative to this, will look like this. Look at that. Yeah, so the left-hand side here, this is exactly the statement above the cone. It's this inequality with square roots. And the second inequality here, it's inside the sphere. It's under the northern top hemisphere. Sorry, under the top hemisphere. So this is the description for the same object, for the same ice cream cone, but which is expressed using the explicit inequalities with z. And such description is the best suited to find out the projection. Because look at this. The projection is it spins around this existence of the z. And when you have a description in this form, the existence of such z is just verification that there is a room between this and this number to squeeze that z. So my projection then takes this description. Look at this. It's all those x and y's, where the left-hand side here does not exceed the right-hand side. Because if it doesn't, you can have a gap in between, and that will be your opportunity to find that z for the projection. So all we have to do now, we have to rework this inequality into something which we can use to identify the shape at the bottom here. And that's what's happening at the bottom here. Look, just for the simplicity, I introduced this assumption. Just call this square root just u, just to make the workings a bit simpler. If I use that, then look at this. My p will take the following shape. I mean the right-hand side of my apologies, will take the following shape. That's the u, and that's the a plus a squared take u. If you work on this expression, if you first move this a on the other side, square it, and then expand and move everything on one side. That's the remaining inequality. After all of the transitions, that's the inequality you're going to have in the simplest possible form. And this is something we know how to solve. That's the parabolic inequality. It solves into this double inequality, u between 0 and a. If you remember now that u was this abbreviation, your final description for P, for the projection, is like so, which we can recognize here. We can recognize here a disk of radius a. And that's how you deliver this projection in analytical terms. Thank you very much. This is it.